No polynomial review would be complete without looking at the graphs of these different polynomials, and there's a very good chance that something like this might be on your test, so make sure that you're familiar with how to graph these different functions and their general shape. Graphs of polynomials are very important as you move into analysis, especially with modeling data points like regression models. And so graphs of polynomials of degree 1 or degree 0 are linear. Graphs of polynomials of degree 2 are quadratic. The graphs of polynomials are smooth and continuous curves. If you look at all the examples here, the graphs never have sharp corners, they never stop, they all have these assumed continuations in the direction they're going. So if you see this trend, you assume that all of them will continue that trend out to positive and negative infinity in their domain and their range. I want to point out some patterns that hopefully you notice. Any odd degree polynomial has end behavior that is opposite. So degree 1, degree 3, and degree 5 all have opposite end behavior. It all starts from the bottom left and leaves from the top right. Any even degree polynomial, like x squared and x to the fourth, starts in the top left quadrant and leaves in the top right quadrant. It has similar end behavior, meaning the arrows are tending toward the same general direction. Go ahead and try and graph these on your own. Just take a minute, draw them yourself, get comfortable with drawing smooth, continuous function curves. This will sound weird when you're hearing me say it, but this is going to help you a ton as you move into your next classes. Recognizing graph patterns is going to be a huge benefit to you as you move through your classes. Notice that all of these polynomials have domains that are on the interval from positive to negative infinity, or if you think about it from left to right, negative infinity to positive infinity. We also use the phrase all real numbers, which is this double-lined R. This means everything on the number line from negative infinity to positive infinity. So knowing that this is the symbol for all real numbers will be helpful as well. Polynomial functions are functions in which ordered pairs are determined by evaluating a polynomial. Now, we went from just expressions to functions, just like that. As soon as we connect a polynomial with a p of x or an f of x or a g of x, we've turned it into an input-output function. If I were given p of x equals x squared minus 3x plus 5, or p of x equals negative 5x to the third plus 3x squared minus 4x minus 3, we would know that these are quadratic. They are not linear. They have a curve, they're not a straight line. To evaluate a polynomial function, we just substitute a number for the variable. And we've talked about this before, but in place of x, we put some other number. So let's say we're going to let x equal 2. Then everywhere there was an x, I'm going to put a 2. And sometimes it's helpful just to write everything else in black, a black marker, and leave an empty space. It's just like a holding pattern for the number you're substituting in. Use a different color. You're just doing a substitution. We're letting x equal 2, so our function p should give us 4 minus 6 plus 5. Simplifying the right side, p of 2 is going to give us negative 2 plus 5. And simplifying further, negative 2 plus 5 is 3. Let's evaluate this polynomial at x equals 2. I just gave you an example, so go ahead and pause the video and give this a try on your own. Welcome back. My first substitution will be p of 2. I need to find the value of the function p when x equals 2. Therefore, I get negative 5 times 2 to the third plus 3 times 2 to the second minus 4 times 2 minus 3. Notice that my substitutions are showing up inside parentheses. This is good form. I am really looking forward to seeing good form when I look at any work that you do by hand. If I substitute that 2 in, I will have negative 5 times 8 plus 3 times 4 minus 4 times 2 minus 3. This will give me negative 40 plus 12 minus 8 minus 3. This is equal to negative 39. Now I'm going to work on part B. B says evaluate p of negative 2. So I'm substituting negative 2 into the function given. Once substituted, I can just calculate negative 5 times negative 8. Negative times a negative gives me a positive. A negative 4 times a negative 2 gives me a positive 8. And negative 3 just drops down. So I have negative 5 times negative 8, which is positive 40. Positive 3 times positive 4 is positive 12. Positive 8 drops down, minus 3 drops down, and now I just simply calculate this. This equals 57. Let's do one more substitution. Let's do p of 0 and calculate the value of p at x equals 0. That substitution will look like this. P of 0 equals negative 5 times 0 cubed plus 3 times 0 squared minus 4 times 0 minus 3. Now, I am doing all these calculations on purpose because I want to make a point. When x equals 0, all of the variables or terms with x in them will go to 0. They will equal 0 because 0 times anything is 0. Therefore, the answer to this has to be p of 0, or the function p evaluated at x equals 0 equals negative 3.